massimo e si spera che la partecipazione
insomma, come dire, lo so, io mi dovete convincere perché
Good afternoon. I'd like to get started. We're here for a briefing on the 2016 Central Italy earthquake. I'd like to welcome the people in the audience and also our viewers in the online webcast. Thank you for joining us. I'm Jonathan Stewart. I'm a faculty member here at UCLA, and I was the leader of one of the reconnaissance teams to do work in Italy, the GEER team. Let me introduce the various organizations that conducted this reconnaissance. They are GEER, which is the NSF-sponsored Geotechnical Extreme Events Reconnaissance Association, EERI, Earthquake Engineering Research Institute, ReLuis, which is a consortium of universities doing earthquake engineering research in Italy, INGV, which is something akin to the U.S. Geological Survey operating in Italy, responsible for ground motion networks, geologic mapping, and things of that sort. Also the EUcentre, that's at the University of Pavia in Italy, another research organization. And I also want to recognize the sponsorship of some of the reconnaissance activities by the Risk Institute here at UCLA. This event is sponsored by most of those organizations. They're listed here, along with the Pacific Earthquake Engineering Research Center and the UCLA International Institute. So I'd like to thank all of the sponsors for their support today. Before going further, we have invited the Consul General's office to prepare some opening remarks for our event today. And so I would like to welcome to the stage Ms. Valentina Gambaluge, who is the Deputy Consul General of Economic and Commercial Efforts here in Los Angeles. Welcome, Valentina.
Dear Professor Stewart, I am honored to participate in this event on behalf of the Consul General of Italy, Mr. Antonio Verde. He asked me to thank you for the kind invitation and to give me the opportunity to attend a briefing on issue of great relevance for Italy, and to thank the University of California, Los Angeles, for hosting this important event. He also wishes, of course, to thank all of you for the tremendous work you are doing and have done in the wake of the Amatrice earthquake. Earthquakes are one of those things that Italy and California share. Although we are happy to concede that California's seismicity is much more famous than ours, nobody has ever made an action movie about our local fault. Seismic events occur from time to time throughout the world, but unfortunately, Italy has frequently paid a high price in terms of destruction of human lives and things, often priceless cultural artifacts. As you know, in the last few days, that area of Italy has experienced more quakes, quite strong ones, fortunately without the dire consequences the previous one had in Amatrice, Accumuli, and Arquata del Tronto. Even when such destruction occurs, it has been possible to reduce its impact and promptly provide assistance to the peoples, thanks to the experience already gained in these fields by our civil protection and its readiness. The above-mentioned towns suffered many deaths and major destruction. Entire villages were reduced to rubble. These recurrences warrant in-depth studies in order to prevent earthquakes' disastrous consequences and to minimize their effects on people, towns, and territories. Part of our work as Consulate General is to foster cooperation between the country we represent and the host country. It is therefore not a surprise that we welcome the opportunity to witness cooperation in this important field. I will let you get to work now, wishing you a fruitful briefing. I am certain that your work together will advance our knowledge of earthquake effects and lead to improved procedures for characterization and mitigation of seismic risk so as to limit the humanitarian impact of these inevitable events. Finally, I thank you to hear me and my bad English. But I'm just arrived in Los Angeles and never worked before in a country where the mother language is English, but French, Arabic. So I will do my best. In any case, I will do my best.
Thank you for your remarks, and I can assure you that your English is much better than my Italian. Okay, so to get us started, this is a map just to show us where the earthquake was. Truly in the central part of Italy. We'll be hearing a lot more about that as we go along. It was on the 24th of August of this year. Various magnitudes have been reported, but the official magnitude from INGV is 6. The maximum intensity is 12, which is extremely severe. And as of the latest count we've received, there were 298 fatalities, which is truly a major disaster by any measure. Just to introduce the teams, again, that were involved, I won't read off all of the names. So this first slide is the GEER team that mobilized. So I was the lead of that team, and we had several people from the US. We had very strong participation from the Italian research community. The lead of that group was Giuseppe Lanzo at the University of Rome. And then we also had, collaborating with GEER, several researchers who've worked with us on various events over the years from Greece and the United Kingdom. The names you see here in bold, you'll be hearing from today, either in person here in CNSI auditorium or through an online connection or a video link. There were the other teams I mentioned in the opening slide. So the EERI team was led by Silvia Mazzoni, who is here. You'll be hearing from her later. ReLuis team members, you'll be hearing from their lead, Masi, and also Sorrentino later. And the EUcentre team members, you'll be hearing from Professor Pena. So just to review our agenda, we have, after these opening remarks, section 3 will be on the regional tectonics and the geology of the region. Some surface rupture, which was a notable aspect of this event. You'll be hearing about that from Robert Cahan. Finite fault model and ground motions from UCLA postdoc Paolo Zimero, originally from Italy. You'll be hearing about the use of drone-based technologies to image some of the damage, both from landslides and some of the heavily impacted villages. And then a discussion of those landslides from Kevin Franke at BYU. We'll be hearing via an online connection about the performance of bridge structures in the area. That'll be from Professor Luigi Di Sarno, the University of Sogno. We'll have 3 presentations related to buildings. Of course, that's what most people heard about in connection with this earthquake and the media coverage. So we'll initially learn about the types of structures that were in the affected area. That will be from Andrea Pena. Then we'll hear about how damage was classified for the purpose of this research and an overview of the regional performance. That's from Maria Giovanna Durante, who is here. And then we'll have a video presentation on some detailed documentation of damage patterns at a high level of resolution from Tasso Sextos at the University of Bristol. Then we'll learn about building retrofit policy and effectiveness. Retrofit's a major story. It was present in some places, not in others. So you'll be hearing about that from Silvia Mazzoni and also Luigi Sorrentino. Then we'll hear about emergency response and recovery, again from Silvia Mazzoni and Angelo Massi via a video connection. And then I'll have some concluding remarks. So with that, I'd like to welcome forward Professor Robert Cahan of UCLA and also of the USGS.
Good afternoon. I'd like to talk briefly about the regional geology and tectonics that led to the character rupture that occurred on the Mount Bové, Mount Vittori fault system. The three Italian partners are Stefano Gori, Emanuela Falcucci, and Fabrizio Galladini. Galladini is a very important character in this story because he's actually the person who did the first mapping of the Mount Vittori fault system and the Mount Bové fault system. So he mapped it, characterized its potential for earthquake rupture, and then in his lifetime has seen that earthquake occur. So the event happened in the central Apennine, and there's a long chain of mountains. We are on the region between Abruzzo, Marche, and Umbria, and the earthquake occurred on August 24th, the magnitude 6 event near Amatrice, and the rupture appears to have occurred on the Mount Vittori fault system. And just 2 days ago, there was 2 new events. There should be 2 stars here. Aftershocks, or perhaps they're a new earthquake on the Mount Bové fault system just north that were magnitude 5.4 and magnitude 5.9 or 6 events, depending on how we measure magnitude. In the Mesozoic time, in the period of 66 million to 250 million years ago, central Italy was a large carbonate platform, very tropical, a zone where we had accumulation of dolomites, marls, calcareous sediment. That sediment lithified into limestone, and this is a typical, for example, South Pacific atoll. This is the kind of environment that that central part of the Mediterranean was in the Mesozoic time. Due to compression that occurred because of the tectonic movement of Africa colliding with Europe, we have a compression zone that has greatly thickened the area in the central Apennine by stacking multiple thrusts of this carbonate material one over the other. So we would say, geologically, we'd say they're imbricate thrusts. They're like stacked roof tiles, imbricated. And that's what we see here in this schematic, which is various sequences of carbonate that are stacked one on top of the other in this central Apennine region. And that was the condition in the Mediterranean Sea until we had subduction down in southern Italy that's opening up the Tyrrhenian Sea and now relaxing the stress, the compressive stress, on the central Apennine. So the central Apennine, which was compressive and forming these thrusts, is now relaxing, and we're having reverse direction of movement, but the faults are called normal faults instead of thrust faults. And that kind of mechanism is seen here. First, we have these packages of thrusts, and then now that we have a relaxation of stress, we have gravitational slippage of blocks as the land is extended or pulled apart from one another. And so there's a suite of thrusts forming down in these lower images. So here's an example of these thrusts. So here, for example, we have a block. This upper part is called the foot wall, and the upper part is the head wall, and it is just gravitationally sliding as this block is extending outward towards the west. And this is the eastern part of the Apennine, which is basically has a rather steep fault system very near the surface. So this might be in the range of 40 to 60 degrees as a fault, but then down at depth, they flatten out, and perhaps in something like allistric behavior, they flatten out, and a number of these normal fault packages coalesce on a allistric fault. So here's the seismicity map for central Italy, and we can see that unlike the United States, we have a very long history of recorded earthquakes that are documented, and the villages that they occurred in are known on this map. They extend approximately 700 years of information. The earthquake occurred in this upper yellow box in this Mount Vittori fault zone, and Mount Beauvais is just off the map up here at the very top edge. You can see that it's not one normal fault that characterizes this zone, but a suite or package of multiple normal faults that can potentially slide, taking the area on the west side of the faults and transferring them downward and westward towards the Tyrrhenian Sea. If we zoom in on the area of the Mount Vittori and Mount Beauvais fault system, we see a gap between the 2009 L'Aquila earthquake that occurred very damaging in Abruzzo state, and then the 1979 Norcia and the 1997-1998 Umbria-Marche seismic sequence or seismic sequence of events that occurred in this upper region. So we have a gap between these events, and the Mount Vittori rupture that occurred on that fault system filled in this gap. And you can see actually that a number of these earthquakes are happening along segments of normal faults. And so when one earthquake occurs, it loads the adjacent fault zone to potentially raise its probability of a future event. So we have a sequence of these earthquakes running up and down the central Apennine, releasing stress on various portions of the region. So here again, filling in the gap between L'Aquila and the Umbria-Marche events is the event from August 24th. So the earthquake rupture occurs at some point on the fault plane, and we call that initiation the hypocenter location of the fault rupture, and directly projected above it is the epicenter, which is the surface projection of that fault rupture, and then some area on that fault plane is slipped during the event. At the very surface, we may see no expression of faulting, or there might actually be a surface break. In the case of this event, there was about 5 kilometers of co-seismic slip that occurred on the surface that was observable. So these normal faults in the central Apennine, this is what they look like. It's a very dry and alpine environment. There are not a lot of trees, so the normal faults are very readily visible. So here we can see fault scarps running across various mountains like Mount Grana Sassa and other mountains in the central Apennine. And the one that ruptured during the August 24th event is along the flanks of Mount Vittori and Mount Redentore. So this is actually the Mount Redentore side of the mountain, and this area is a large agricultural plain that sits below the mountain. And just from the car, as you drive into the valley, you can just clearly see that fault break across the upper flank of the mountain. You can also see a second normal fault that's halfway up the mountain that was not involved in the slip, and there's a third normal fault at the base of the mountain. So any one of these is potentially a source for earthquake motion. This happened to be the one that led to the triggering of that event. So Galladini and Galli mapped these faults in the Norcia region. Norcia is a large city that sits right off here to the west of these fault systems. So here's a suite of normal faults that are in this Mount Vettori region. This is the Castelluccio plain that we saw that last picture looking across at Mount Vettori, and the normal fault that you could see that ruptured is this upper fault, most eastward fault of the normal fault sequence. One method to measure deformations of the surface from earthquakes is from multiple passes of satellites. So this is a synthetic aperture radar image of coseismic deformation of the ground. And what we can see is multiple fringes in this fault zone between the Mount Vettori fault system and down to the south, the very north end of the Laga Mountain fault system. And Amatrice is sitting right here at the southern end of this rupture. A combination of INGV geologists and the GEER team made many observations along the surface rupture of the Mount Vettori fault, climbing up over the saddle from this highway crossing, and then up at high elevation following that normal fault along just below the summit of Mount Redentori. So here you can see the eastward fault and the second one eastward projected to it and adjacent to it, and this one to the east is the fault that ruptured. We can see visible as we visit the fault that ruptured that there's clearly a large offset that represents many earthquakes of deformations, perhaps something from the late Pleistocene time to present, something like 8 to 12 meters of offset between the downdropped western block and the eastern block, the footwall and the hanging wall of the fault. So this portion where everyone's standing here on the left side has gone down relative to the fault, to the hanging wall on the right. And there's Galladini telling us about the characteristics of this fault on our first day in the reconnaissance. This is what the fault break looks like. So here is the actual slick-sided fault plane surface in the upper left, and we can make measurements of how much slip occurred on the surface at all of these points along the fault rupture. And what we see from bringing these data together is that the range of slip that occurred on the fault is between no slip at all and 25 centimeters of the hanging wall down to the west. The average dip angle of that slip was 52 degrees, and the average strike of that slip was 158 degrees, or south 22 degrees east. In some cases, the slip break occurred adjacent to the fault rock, and it broke through soil. And so these are examples of surface rupture through soil and immediately adjacent to the rock. This is just a thin veneer of soil sitting on top of the bedrock. And here, too, you can see the fault rupture underneath our feet, right at the base of the bedrock fault plane, And again, everything off to the right has slipped down somewhere between 0 and 25 centimeters. In this case, we see that the soil that's accumulated against the fault plane has slipped something like 20 centimeters, and it's exposed something like a soil line on the fault plane. So we can see how much coseismic slip has occurred by measuring this zone where the soil was pulled away from the fault plane. When we look at this event and we plot it against other known and characterized earthquakes, we find this actually a rather normal or typical earthquake event. So in this case, we're plotting moment magnitude of the earthquake against the surface rupture length, and this is a seminal paper by Wells and Coppersmith, and we find out that for its magnitude, it's absolutely typical predicted level of surface rupture. Likewise, if we plot average displacement of the event against its surface rupture length, again, it projects out as a rather typical magnitude 6 event. Okay. Next. So our next speaker is Paulo Zimmerau. And Paulo is a postdoctoral researcher at UCLA.
Thank you, Rob. Thank you so much. The presentation that I'm going to make deals with finite fault model and ground motions, and it is actually linked to what Rob was just talking about. So first of all, I would like to, one second. There we go. First of all, let me acknowledge several people that enabled this presentation. It was really a collaborative effort, and as you can see, a lot of people contributed. For the ground motion part, I would like to thank Giuseppe Scasserra, Filippo Santucci de Magistri, and Massimina Castiglia from University of Molise, and Tadahiro Kishida from UC Berkeley at Pier, Stefano Gori, Emanuela Falcucci, and Fabrizio Galadini at INGV, and John Stewart at UCLA. And of course, I would like to thank all the GEER team members because it was really a collaborative effort. Let me start from where Rob was actually leaving the stage. We are dealing with normal faults, and as you can see here, we have a sketch of a normal fault from the website of USGS. I would like just to point out that we have two different parts of the fault, which are the footwall and the hanging wall, and this notion will be useful later when we will be dealing with distance calculations. Rob was actually describing the Apennine chain, which runs along the whole country from north to south, and it appears like a long red line. But what it is actually appears to be, it is rather a series of faults and segments that are usually not connected, and this is where the so-called segmentation comes to play a role. And as you can see here, the red square is the epicenter, more or less, of the 2016 earthquake, which lies right between the Monte Vettore fault and the Laga Mountain fault. So this recalls and reminds us that there is a potential in this area for an earthquake to be triggered on a fault and jump on another one. This is something that we refer to as the multi-fault or multi-segment ruptures. So why this case history is important for us? I mean, why this is of interest for from a global perspective? First of all, here in the US, there is the presence of many normal faults that are running from the orange shaded area here, more or less, which is the eastern side of the Sierra all the way to Colorado. We have a series of normal faults, so this is very important. And in this area of the United States, there is a presence of critical infrastructure. Another important point is that in empirical recording databases, and here I'm referring to the PEER and GEOS2 empirical database, the 40% of the total recordings and the 64% for magnitude greater than 5.5 from normal faults are from Italian earthquakes. That's why Italian earthquakes are very important and globally relevant. And that's why GEER and other research institutions from the US and from other countries, of course from Italy, deployed a lot of people trying to learn something from this earthquake. So as you can see here in this slide, I'm plotting the near source recording stations. This point, the beach ball, is the epicenter of this earthquake, and the colored circles are the peak ground acceleration that was recorded at the recording stations that are present and deployed throughout the area. As you can see, and this is something that I will underline later, we have a pretty localized kind of shaking here, and I will come back to these. So, as you can see here, we have several recording stations in the area, so we decided to go there, visit the recording stations, and see if the locations are okay or if there is damage. And we were able to get to the Amatrice AMT station, which is here, south of the rupture. And then we went to Norcia, which is actually hosting many recording stations on NRC, NOR, and there is another one up here, which is on NRCA, which is white, because it provides, unfortunately, it didn't work during the main shock because of a power outage. And something that is we are working on is why there is an erroneous horizontal component for the RQT station, which is very important here because it's the only one in the near field on the footwall. And so that's why it was important to get there and to take a look to all these stations. As you can see here, there is a zoom out picture of the peak ground acceleration spatial distribution. And again, the blue dots are representing a fairly weak motion, while red to green and orange are a higher level of shaking. As you can see here from this better overview, the spatial distribution was very localized of the shaking. So in order to understand better why we observed this localization, we decided to look through the finite fault model, which is the portion of the fault that actually broke. There are several methodologies that can be applied. You can use ground motion data, and here I have an example picture from Tindy et al. 2016. And there, you can take a look to the geodetic data from INSAR or from GPS, and this picture on your right-hand side is showing an image from INGV. The red arrows are representing horizontal coseismic displacement. The blue ones are vertical coseismic displacement. As you can see here, the first preliminary 3D model that was developed by INGV researchers is actually showing a very nice feature, which is something that we will look closely later. There are two main slip patches, here on the north side and here on the southernmost side, and this is the hypocenter where the rupture started. The maximum slip is around 1 meter, and the deep angle, consistently to what Rob was underlining, is around 50 degrees. So this is a newer model for the finite fault solution, and it is from Tinty et al. 2016. It is a recently published paper. And as you can see here, again, this is the epicenter, which is the surface projection of the hypocenter. This slip patch is very close by Amatrice, and there is a second slip patch, which is close to Arquata del Tronto, Pescara del Tronto, and Montegallo. So this is something that could explain why the strong shaking that we see here was very localized. And later on, you will see the structural damages and the seismic related landslide and rockfalls. And you will see that all these damages were localized mainly because the shaking, the slip was localized. The slip is actually representing the relative displacement of a site of a fault relatively to the other. So that's a very important takeaway from this figure, from this slide. Now, there is another important point why the finite fault model is very important for us, because if you take a look to the ground motions, we need to calculate the source to site distance, which is a very important thing. So once we have the finite fault model, we can calculate easily the distance between the fault and the recording stations. And then we can perform ground motion analysis. On the left-hand side, you can see several metrics of distances. The one that I'm going to use in the next slides is going to be RJB, which is the joiner and bore distance. And using this distance metric, I will show you some comparison between data and predictions. So let me go really quick on this slide. These are acceleration time series for the same recording stations that I was showing before, AMT Amatrice, Norcia, Annersea, and Norcia Nor. As you can see here, the horizontal component in Amatrice and Norcia has a PGA of around 0.4, 0.37, something like that. The vertical component has a weaker shaking. I can anticipate that this is not an unusually strong shaking for a 6 magnitude event. It is rather kind of typical for this kind of events. And if we compare these with something that happened in 1994 Northridge event, these are fairly weaker strong shakings by about a factor of 2. Going through the response spectra, which are representing on a certain extent the response of a simple structure in the frequency domain, we are actually showing these spectra for the same stations as before. And the red lines are the fault parallel and the fault normal components, and the gray dotted line is representing the average of the two. As you can see again, the level of shaking was not unusually strong, and I will show you why later. In order to do that, we have to use ground motion models that are used usually to predict seismic hazard and seismic risk for extreme events. So I will show you some comparison between ground motion models, so the prediction and the actual data recorded for this event, but this is not the main purpose of these models. These models are usually used to forecast extreme events, risk and hazard. Here you have the database from NGA West 2, which is a global model, meaning we have data points from everywhere in the world, against the database of Bindierol 2011 ground motion model, which is an Italy-specific model. So there are, as you can see here, the horizontal scale is different. Here we go up to 1,000 kilometers, while here we are to about 100 kilometers. So the scales are different, but the takeaway from this slide is that you can have a lot more data from global models. The trade-off is that you lose, to some extent, the possible regional features that are typical of a region, which is better captured with an Italy or a regional specific model. On the other side, regional specific models have a lack of short distance recordings and high magnitude recordings, while this is not happening for global models. So there are legitimate reasons to prefer one or the other. In this slide, I'm showing both the Bindierol Italian-based model and the BSSA 2014 NGA West global model with a regional adjustment for Italy. As you can see here, again, this wasn't an unusually strong earthquake. Rather, the models are actually capturing very well the trend of the data. either for PGA, so the peak ground acceleration, and for the peak ground velocity. As you can see here, I'm plotting also plus minus the standard deviation for this prediction based on the Bindi et al. 2011 model. And as you can see here, we are actually nicely capturing a lot of data. There are a few outliers, but overall, the shaking was something that we could predict beforehand. A nice feature that is actually showing up here, taking a look to these data, is that Italy, and this is well observed, has a steep attenuation with long distances. And this is something that we can see on the end of the data, where the curves are stopping. So this is a very interesting feature, but again, this is something that we can predict. This is something that wasn't unusually strong. And later on, you will see other presentations that are showing damage patterns, and you will recognize these localized effect of these earthquake. And this is all. Thank you so much.
Okay, so our next speaker will be Professor Kevin Franke.
Okay. Thank you, everybody. It's a pleasure to be here from Brigham Young. I'm here to speak today a little bit about applications of using unmanned aerial vehicles, or commonly referred to as drones, in post-earthquake reconnaissance, and specifically how we used these robots in Italy to image and model landslides. I want to first acknowledge, of course, the organizations that made this aspect of the reconnaissance possible, the NSF and GEER, also the NSF-sponsored Center for Unmanned Aircraft Systems, and our research colleagues at the Politecnico di Torino in their geomatics group. So in terms of overview of the landslides, when the GEER team was selected and we were asked to go to Italy, we already had a lot of information regarding landslides. A lot of existing information was available from numerous sources, including CERI and ISPRA, and they were able to map and document several landslides and rockfalls. Now, most of these rockfalls were very small in nature. They were more unraveling of rock onto highways and roads. And in addition to that, NASA Jet Propulsion Laboratory provided an INSAR, or interferometry, synthetic aperture radar, damage proxy map of areas that they felt could be possible soil deformations or rockfalls. And so when we evaluated the damage proxy maps, what we really saw were hundreds of potential landslides. And we didn't have enough time to visit all of them. As a result, we had to make some decisions. We decided to focus principally on large landslides, or slides that we felt like were going to be impactful to infrastructure. And we chose 5 specific areas to focus on. The first area was just north of the town of Cittadella, and then another cliff north of Pescia, the town of Accumoli, the town of Pescara del Tronto, and also a highway section, Highway SP 477. These were the areas that we were going to go and visit. We wanted to use drones to be able to monitor and image all of these landslides and see what we could do with the data that we collected. The specific goals for using our drones were many. First of all, we wanted to, of course, obtain valuable visual data that we'd be able to share with other people. And what was important here is that you need to understand that this is very difficult and challenging terrain. It can be difficult to climb and get to the areas we're interested in, but there's also lots of vegetation that prevents us from getting where we want to go. So the drones were going to be very useful for us. We also wanted to stay out of the way of emergency responders. We were arriving pretty much just about 10 days after the earthquake event, so a lot of the emergency responders were still doing their jobs, and we wanted to stay out of their way, and so the drones were going to let us do that. We want to be able to collect more data and more valuable data in less time, which of course then will allow us to visit more potential damage sites, and we can collect more information from more sites in less time. We want to share the imagery that we collect with the drones with the necessary and government agencies that can use that imagery to make decisions. And then finally, we wanted to take the imagery from these UAVs and model them in a three-dimensional manner to make publicly available three-dimensional models that researchers and students from all over the world can utilize and learn from. So these were our goals. I'll introduce you to the drones that we used on this reconnaissance mission. So our collaborators at the Politecnico used a SenseFly EB drone. This is a small fixed-wing drone that is very light and portable. It has great battery power in the sense that it can fly for up to 40 minutes under ideal conditions. It uses a Canon PowerShot digital camera that's mounted on the belly of the drone that's pointed straight down. And so as it's flying, it's able to take images of whatever's directly below it. One of the fun things about this particular drone is that it's completely automated. And so all of the waypoints were pre-programmed into its autopilot, and it basically takes itself off and lands itself after it's collected all of the data that it needs. From BYU, we used a couple different platforms. The first platform I introduced is a platform that many of you may be familiar with because it's very popular. It's the DJI Phantom 4. This is a very affordable quad-rotor drone. Nothing really special about it other than it's very reliable and fun to fly and gives you good data. It's small, and so it's very portable. It has autopilot and waypoint capabilities like the EV does, but we were using it in a manual method with a trained and experienced UAV technician, and we were flying it with first-person view. That's where the imagery is transmitted directly to the operator, so we can see in real time what the drone is seeing from the air. And then it's using an adjustable 4K video. One of the nice things about this type of platform is that it has an image stabilizing gimbal so that the imagery is nice and crisp. One of the problems you have with fixed-wing aircraft is that the imagery can be really bouncy and jittery, which can have implications and problems with your post-processing and your modeling. The third drone that we used was an Align T-Rex 800 that we customized at BYU for aerial photography. This is a large UAV. It's classified as a small UAV, but make no doubt about it, it's large. It has a blade diameter of about 7 feet, and it carries a full-size Nikon DSLR camera. So basically, its operating payload is about 10 pounds, and it can carry up to 20 pounds. Because it's carrying so much weight, its flight endurance is a lot shorter, 12 minutes on average. But one of the nice things about this particular platform and why we wanted to bring it with us to Italy is that because this spinning blade has such a large polar moment of inertia, it's basically unfazed by winds up to about 50 or 60 miles per hour, which means that in very windy environments, we don't feel it, and it can operate in a stable manner. And so that came in handy, as you'll see here in a minute. I want to demonstrate and just show you some of the drone footage that was taken. Now, this drone footage was was cropped down and is available on YouTube. You can access the link from the GEER webpage for the event. And we're not going to watch the whole video, of course, but I just want to show maybe a couple of the types of imagery that you can get. So this is imagery of the village or the town of Akumali. If I go back just a little bit, you can see some of the damage patterns in the ground in Akumali. If I scoot forward, so this is aerial imagery from the town of Pescara del Tronto, a very heavily and damaged and impacted town from the earthquake. Landslide below Pescara del Tronto. And so this is about an 8-minute video. We have close to 50 gigabytes of video, I would say, that we've turned over to GEER, and is basically available to the public for the raw images. And so that's there for anybody who's interested in seeing it. So one of the principal things that we wanted to do with this aerial imagery is structure from motion computer vision. Structure from motion computer vision means we want to make a 3D model from the imagery that we've collected. The way structure from motion works is the same way that your brain works when it sees 3D imagery. So for instance, you could take an object that may be recognizable, such as the Sydney Opera House, and you can imagine that there are images or two-dimensional pictures of this object from every possible angle that are out there and that we could look at. And you could look at any picture of this structure and immediately you recognize it for what it is, no matter what angle you're looking at. And the reason that this is the case is because you can see several features, for instance, these points on the structure that stand out to you. So when you see those points and in those patterns, your brain immediately recognizes, oh, that's the Sydney Opera House. So what if we could train a computer to be able to look at a series of images, and the computer can figure out that this point is the same as this point, and that this point or this object is the same as this object, regardless of what direction or angle we're looking at it. As soon as the computer can figure out and isolate specific objects, then it can start to back calculate and triangulate the location of the camera relative to those points. And so by back calculating and triangulating the location of the camera, essentially structure from motion has now developed the third dimension, from which now we have depth and we can create a 3D point cloud of whatever object that we're trying to model. An important feature when we try to georeference and make accurate structure from motion computer models is ground control. Ground control points provide basically a check for our models and provide anchor points that will allow the model to be scaled accurately and will speed up the processing and essentially georeference and straighten the model, prevent it from being warped. So our collaborators at the Politecnico brought their surveying equipment, and they were able to lay out ground control points in Akumali and Pescara del Tronto. And those ground control points consisted of both artificial markers as well as natural markers that were going to be very easy to see and visible from the air. Another technology that assists us in structure from motion computer vision is the use of geotagging of our photos. So if we have a GPS tagging device attached to our camera, and every image that the camera is taking is being tagged with the approximate location of that camera, we basically make it easier for the structure from motion algorithm to know where every photograph is being taken from. And it speeds up the processing because it gives it an initial estimate for the camera location for every shot that's taken. The problem with this is that the benefit of using this tagging device may be outweighed by the lack of accuracy of the GPS device. So if the GPS device is only accurate within a radius of 50 feet, then it may not help us much at all. So now I want to just summarize a few of the observations we had regarding the landslides and the use of drones. Let's start with our observations from Città Reale. When we went to this location, there was a large indication on the damage proxy map that deformations occurred in this area. We pulled in on the road right down here below. There was no way we could see it with our eyes because it's way up above all this tree cover. We put the drone up, and within minutes we could see there was nothing there. There was no visible earthquake-induced landslide. That was extremely helpful for us because within 5 minutes we could pack up the car and move on to the next site. When we went to Pescia, we noticed that there were indeed indications of earthquake-induced rock topples and rock falls. You could see by the lighter color. I want to point out, by the way, that this image is not a photograph. This image is a still image from our 3D computer vision model. And in fact, all the remaining images you'll see in this presentation are not photographs, but they're stills from our 3D models. So you'll see just how nice they look. We saw significant earthquake-induced landslide features in the towns of Accumuli, Pescara del Tronto, and along Highway SP 477 that I want to talk about right now. And I just want to take this time right now to say that the drones were really an invaluable reconnaissance tool for us and allowed us to get a lot of data that we otherwise would not have been able to obtain during this reconnaissance. So let's summarize the observations we had in Accumuli. First, the EB drone from our Italian collaborators developed a very nice ortho photo, a much higher resolution than what we get from satellite imagery. So this could be useful for two-dimensional image analysis. When we arrived later, there was an important government meeting going on in the city, and we were only granted authorization to fly over the western portion of the town. They wouldn't let us fly over the rest of the town. But that was okay because this is where the landslide was supposed to have occurred. And so we were able to fly over that portion of the town, collect the imagery, and make the model. The model did confirm that landslide had occurred below the eastern portion of the city, as can be seen from this cracking right here in our 3D model. The widths of those cracks range anywhere from 5 to 20 centimeters in width. Another feature we thought was very interesting from Accumuli was retaining wall failure. And that's not really the topic of this talk, but it is still cool to show that our 3D model could pick it up and show great detail like that. Observations from the highway rockfall. We used the big T-Rex helicopter to gather imagery from this site. One of the challenges with this particular site was we only had 40 minutes total from start to finish before we had to leave because the sun was going down. And so we had very low light conditions. As a result, we had to adjust the camera settings to try to let more light in, but when you let more light in, the shutter is open longer, so a lot of our images were blurry. And that did have an impact on our model, but we were still able to get a decent model out of it. Also, because we were in a hurry, it was Friday, the night before we were flying out, our Italian collaborators had already gone home to Torino, and so we had no ground control points at this location. But the model is still scaled pretty accurately from the GPS. We were able to investigate from this 3D model some very interesting things. We could see boulders on the road, and because we're using the drone up in the air, we could see the pathways that the boulders took on their way down. This is one of many possible pathways, but you could see how this boulder may have split and separated into several boulders on its way down. One of the scary things after I started investigating this model was finding this boulder right here. Paulo, did you have any idea that that thing was right above us? You can see here's our car. It's about the size of our car, completely hidden in the trees. Well, there it was. We had no idea it was there. Kind of dangerous, but anyway, we left unharmed. So these models can be very, very useful for us to measure and try to learn more about how boulders and rock falls can occur and predicting where boulders are going to go. Observations from Pescara del Tronto. Again, we use the EB drone, or our Italian collaborators use the EB to make a nice ortho photo of the city. Excuse me. The city was essentially on lockdown by the military and the fire department, and we were not granted a lot of time to get in there and to perform our reconnaissance. They gave us 2 hours to reconnoiter the entire city. So drones were extremely useful and valuable for this. Because of this, we used the Phantom with the 4K video. And from the resulting images and models that we developed, we were able to go back and basically perform our reconnaissance after the reconnaissance, if that makes sense, and go in and look in the models and see several landslides that we had no idea were there, and we're able to make very detailed and accurate measurements from these landslides. We saw from this town that the interactions between retaining walls and landslides are going to be a very interesting thing to look at from this earthquake. And certainly there's a lot of story to be told here and things to learn, I think. My time is running short. I want to just say that these models are out there. These models are available for you to see right now. If you have a smartphone in your hand, you could go to any one of these web addresses and pull up the model right now on your smartphone and play with it. And I'll prove it to you. If you go to, for instance, here's the model for Pescara del Tronto. And so these could be excellent teaching tools. These could be excellent tools for researchers around the world to be able to see and learn from these different landslide features. So we're hoping that by making these types of models available that we essentially establish a new bar as far as what type of information and data becomes available from these geotechnical reconnaissance missions. And by sharing this type of information openly and freely with the world, we hope that a lot more interaction, questions, and discovery comes from these types of models. I want to point out as well that we've done several accuracy assessments with the ground control points, and to our best understanding, the horizontal root mean square error is just over 15 centimeters for these models, and the vertical error is just under 8 centimeters. So not too bad. For a lot of structural engineering applications, maybe not adequate, but certainly for geotechnical, they probably will do. In closing, a couple of final words I want to say regarding the use of drones and post-disaster reconnaissance. We've done this a few times now. This isn't our first rodeo. And we've found in every single instance that obtaining authorization to fly before we arrive in the country is always a challenge. And that's putting it kindly. We found that having relationships with influential agencies and decision makers in those countries really makes a difference. Transporting the drones can be a hassle. The small ones aren't bad, but the big ones can be, especially because of the batteries that you have to take with them. You can always plan on having technical glitches and malfunctions. It's just, you just plan on it. And so it's helpful to have a technician in the field who can deal with those issues. Because even the commercial off-the-shelf stuff tends to break. And finally, we just want to say that the 3D model accuracy, like the model I just showed, is really a function of the type of equipment you're using, the altitude or how high you're flying it off of the ground, and whether or not you have ground control points, which just means more equipment that you have to haul to the field. And so if you are performing post-disaster reconnaissance, you really need to give some thought and decide and do this balance. How much accuracy do we want in our models versus how much equipment do we need to take with us? And that's really the question that we need to ask. So with that, I want to thank you for your time. And I'd like to turn the time over now to, let's see, who's speaking? It's Maria. Okay, so I'll turn the time over to Maria Giovanna Durante. Thank you.
So we're going to establish a connection to Italy now. It's a little bit late. Are we advancing the slides here?
Hello?
Hello. Good afternoon. Can you hear me?
Yeah.
So we're going to establish a connection to Italy now. A little bit late.
Okay. Can you hear me?
You should mute his line.
Ok. Pronto? Sì, sì. Sì, ma deve togliere il computer. Ok? Pronto?
So while she's establishing the connection, he just needs to mute his line. We're going to be hearing next, this is section 6 on the performance of bridges. So we had a team of people going out pretty much every day that we were there looking at bridges. Italy has, in this area, has a combination of fairly modern viaduct type structures and then also some very old masonry structures.
Ok, now we are ready.
Okay. Good afternoon, everybody. Can you hear me?
Yeah?
So while she's establishing the connection, he just needs to mute his line.
Okay.
We're going to be hearing next, this is section 6 on the performance of bridges. So we have people going out
Hello? One moment. Ma si sente? Sì. Ok. I think that there is a problem with the microphone. Okay.
So good afternoon.
Okay.
My name is Luigi Di Sarla. I am assistant professor in electrical engineering at the University of Sagna and associate researcher at the University of Naples, Federico II. And I have participated to the earthquake reconnaissance as a member of the ReLuis consortium, which is headquartered in the University of Naples. First of all, I'd like to express my special thanks to all participants of the GEER group members and the EERI group members. Today, my duty is to report briefly on the bridge performance. Both resilient lifelines, roads and infrastructures are essential for communities, especially in the aftermath of seismic events, because these infrastructure allow rescue operations, like, for example, they allow driving people to hospital if they are injured. And in this presentation, I'm going to focus on few examples of bridge performance, including masonry, primarily masonry and reinforced concrete bridges. So, as you see from the slide, the area that has been stricken by the earthquake, yes, it is characterized by a number of roads, as highlighted in blue, particularly very close to the epicenter of our fissure, where minor and also important roads are built, and they are characterized by a number of bridges because of the orography of the site. And some of these bridges have experienced damage because of combination of low maintenance in some cases and also earthquake-induced effects. So now we'll be looking at the roughly 10 bridges that we have been surveying, during the reconnaissance, and they are here located with respect to the seismic faults. You see that some of the bridges that we have been observing in the aftermath of the earthquake lie very close to the fault of the earthquake, and then they also were highly affected by the seismic effects. Some others are located further, going towards northeast, but they were also affected to less extent by earthquake damage, primarily from the geotechnical point of view. These bridges that we are going to discuss today were the ones that are made of concrete, reinforced concrete, were primarily built during the 60s. So some of them, they did not really employ seismic details, and in fact, they were primarily designed for gravity loads. This also applies to the old masonry bridges that we inspected. Some of them were closed soon after the earthquake, and they caused major problems for the accessibility of the areas, particularly for the rescue operations that were needed in the aftermath of the event. Let us start with the so-called Ponte Andreotti, the ice bridge. That is one of the crucial access points to Amatrice. This system is characterized by 3 arches, as shown from the aerial view that is provided on the left side of the slide. And these 3 arches are made of clay bricks. And there are also large, heavy river stones that are used to fill the abutments and the arches. The major damage that was observed for this bridge is located on the surface, on the road surface, as shown in these photos, where you may observe large cracks that are located primarily on the roadway, on the 2 lanes, and they're creating large segments of the pavement, as shown also by the meter. In fact, we collected data, and we had something like 10-15 centimeters of displacement of sediment. And as you see also on the right side of this photo, there was a measure that was used to see if there was any progression of the sediment during the different days after the earthquake. The damage that has been observed on the top of the surface has caused major lateral spreading. Now let's move on to the next slide. And in fact, the buttresses that were present on both sides of the bridge show large cracks. In particular, they failed because of shear. The failure mode that characterizes buttresses is sliding, and in fact, it creates the large crack on top of the buttresses, as shown on the left side photos, and also in the middle. And the reason for having such failure mode is because here we are talking of simple concrete without any steel reinforcement. So the lateral spreading has caused large troughs. Hence, there was damage that created these huge cracks, as shown here, where, for example, you can even insert your hand in between the 2 concrete blocks. And this is, of course, a brittle failure mode that took place on this side. On the other side of the bridge, there were additional buttresses, but they were made of reinforced concrete. And because of the presence of large bars, there was no such sliding. Then we also monitored the walls, the arches that were made of bricks, of clay bricks, and we discovered traditional diagonal cracks that occurred because of the seismic damage. And as you see from the photo on the right side, this bridge has been, through the years, also has been retrofitted. But the retrofitting measure that has been applied for such bridge probably was not as effective as expected. And in fact, we found that there were transversal ties that were not effective, particularly very close to the abutment. Because of the nature of the rubble that was used for the abutment, these ties were not effective to prevent the lateral spreading. Similar damage was also observed partially in the other bridge that is very close to Amatrice. In particular, it is located near the lake of Scandarello, and this is the so-called Ponte Andreotti. This is another critical infrastructure because it was used soon after the collapse of a major bridge that was initially used for the access to Amatrice to have access also for the rescue operation. So there were heavy trucks that were running on top of this bridge. And as you see from the lateral view of this bridge, its maintenance was rather poor. And in fact, the damage that we have observed, now let's move to the next slide, was primarily concentrated in the zone near, very close to the piers, where, for example, we found trees that were there just because the maintenance was low through the years, and because also of the water that was running from the surface on the top, and the mud that is present in between the rubbles, these trees and all these green were located on the side of this bridge. Another particular aspect to highlight is that this bridge was also, during the years, retrofitted. You'll find, for example, the interior shell made of concrete that was very important for the mechanism that took place for this bridge under earthquake loads. And in fact, if we consider the frontal view of the bridge, we may observe that there are hinges. We are still investigating the response of this bridge, but we suspect that there were hinges that were primarily formed at the intersection between the pier and the arches. So basically, these arches started to move laterally and to form hinges at the connection with the port. And because they were creating large axial loads that were transferred to the piers, there was large compression. And due to the particularly loose characteristics of the rubber, that was used for the infill between the arches, we have seen that there was a lot of damage concentrated at the location between the arches themselves and the piers. And in fact, also the increase of axial load that was inserted into the piers may have caused probably also large cracks that are vertical and that we have observed along all the piers. In fact, we went on site and we started to remove the fence that was covering these piers, and we discovered that there were passing cracks as shown in these photos. This bridge was partially, there was a limitation for the maximum load that it carried, and after the inspection that we carried out, we also advised to start to have a test to determine the residual strength of the piers, because we found all these cracks that were widespread along the piers. Now, there are other bridges that are located rather close to the epicenter. For example, the one that we have observed near the Trevalli, along the Trevalli Impre, that is a main road, SI stands for Highway Road 685. And as you see, this is a multi-span bridge that is made of very stiff piers, reinforced concrete piers. And when we look closely from sideways, we observe that, particularly for short piers, because of the inclination of the decks, there were in some cases hammering between adjacent piers and the cap, the bridge, and the pile, and the pier caps, as shown here, for example, where you see some of the concrete that was observed because of the hammering between the bridge girders and the pier caps. Of course, this bridge was still functioning after the earthquake because the damage was minor. So luckily, it could be used also soon after the major event of the 24th of August. But there were some minor damage that was localized primarily on the surface at the expansion joints. Not far from this reinforced concrete bridge, there was a collapse of another reinforced concrete bridge. And in fact, in order to replace and to reestablish the connection between different parts of the municipalities of Amatrice and surrounding municipality, there was a temporary bridge. So this is part of the recovery that was very quick. This was a steel bridge that had been built soon after the earthquake. It took maybe 10 days to be built, and it was very easy to lay. And it is a span of 12 meters. It's a modular bridge. So you see, for example, on the bottom, the man that invented this bridge that is very famous also for the art, because it is easy to carry, it is easy to install. It is a simple supporting bridge. So we have a roller on one side, we have an inch on the other side, 6 inch on the other side, and it has a wooden deck. It allows the passage also of heavy trucks. Of course, it depends on the maximum weight that you want to carry, and depending on that, you may add additional modular on top of it to make the structure stiffer. And this is part of the work that has been carried out by all the people, the army and the firefighters that were on site, that were very prompt in responding and to reestablish the connection between the different parts of the municipality that were initially disconnected. So this brings me to the conclusion. And I thank you all for your attention. I hope that I met also the time that was allocated.
Okay. Okay, now it's time for the building section.
Close all of this. We don't need any of that. And we want this one.
Good afternoon. My name is Andrea Penna. I have prepared this presentation on building. Good afternoon. My name
It's plain.
is Andrea Penna. I have prepared. Good afternoon. My name is Andrea Penna. I have prepared this presentation. Good afternoon. My name is Andrea Penna. I have prepared this presentation on building construction typologies together with Professor Guido Magenes of the University of Pavia and Professor Luigi Sorrentino of the Sapienza University of Rome. Associate Professor at the University of Pavia, mostly interested in the study of the seismic behavior of masonry structures. And I have some experience in post-earthquake surveys in different countries. In general, summarizing the distinctive features of the buildings in an area with such a long and complex history is a nearly impossible task. But I'll try to highlight some of them. As in other parts of Italy, the major part of the building stock in the affected area is made of old and reinforced masonry buildings. And in these mountain regions, most of the existing buildings are stone masonry buildings. Most of modern buildings have reinforced concrete structures, and industrial buildings are typically single-story precast structures. Despite a seismic history full of large events, the level of seismic protection is not homogeneous nor particularly high. This is due to many factors. Municipalities belonging to different states prior to the Italian unification, insufficient code prescriptions, in particular before the L'Aquila event, and in some cases, lack of control and maintenance. This latter aspect can be associated with the depopulation of these rural areas, with the exception of Norcia, where, thanks to mainly its touristic vocation, we can notice a different demographic trend. In general, based on processing of past post-earthquake survey data in central and southern Italy, we can notice that the larger part of the Italian building stocks along the Apennines is mainly made of low-rise buildings, with stone masonry structure, which is mostly undressed and rubble stone masonry. Looking more in detail at the building stock in municipalities which experienced the highest shaking, Accumuli, Amatrice, Arquata del Tronto, and Norcia, we can first notice the different seismic histories with higher microseismic intensities that is reported in the past in Norcia and Accumuli, where relatively smaller damage were observed after the last August event. With the data collected in the surveys after the 1997 Umbria Marche earthquake, we noticed that most of the buildings in Norcia do not exceed 2 stories, and that rigid diaphragms are not infrequent. Conversely, in Arquata del Tronto, we find buildings with a larger number of stories and lack of tie rods for wall-to-wall and wall-to-diaphragm connection. And accumuli, we have a more complete survey thanks to a national inventory program promoted by the Civil Protection and ReLuis. You can see the center divided in different areas where the buildings are rather homogeneous in terms of structural typology and age. Similarly for accumuli, where you can see also the public buildings highlighted in yellow. The historic center of Amatrice is mostly constituted by undressed or rubble stone masonry with multiple leaves, which are unconnected through thickness, connected by lime or mud mortar, mostly in raw conglomerations. They have been built mostly before 1900. The number of stories range from 2 to 3 generally, and most of these buildings have timber floors and steel beams with clay tiles in a small part. There is the presence of structural vaults, and typically they have masonry shallow foundations. In these pictures you can see the very poor construction quality of these buildings with undressed stones, mud mortar, and multiple leaves unconnected by through stones, which tend to activate section failures and out-of-play mechanisms. These are the typical examples of buildings responsible for the bad reputation of unreinforced masonry. We could find examples of earthquake-resistant EMIT details were not systematic nor effective as those present, for example, in L'Aquila. Typical RC buildings, mostly built since the 70s, are usually made with 3-4 stories unidirectional frames with masonry infills. Post-concrete structures sometimes include design issues and poor detailing, and they typically show the effect of the high vulnerability of the 2-leaf infill walls. Newer reinforced concrete buildings, properly designed and including single-leaf infill walls, don't show the same issues. New reinforced masonry buildings with clay blocks, rigid slabs, and ring beams perform very well with very limited damage. The issue is related to heritage structures, which are often intrinsically more vulnerable than ordinary buildings and hence suffer damage in a much wider area. This is not only a conservation issue, as many public functions are hosted in the heritage structures, schools, hospitals, and city halls. From a structural engineering viewpoint, finding appropriate strengthening and retrofitting solutions for these structures represents an important as well as a difficult task. Thank you all for your attention.
Good afternoon, everyone. My name is Maria Giovanna Durante, and I will present few damage classification and regional performance for building. Before to start, I would like to acknowledge all the GEER team members, in particular Professor Stewart from University of California, Los Angeles, the co-leader team Giuseppe Lanzo from University of Rome, La Sapienza, Professor Shide Dasti from University of Colorado, Boulder, Sebastiano Foti from Politecnico di Torino, and Alessandro Bagliaroli from University of Chieti Pescara. Here there is a brief description of my presentation. I will focus mainly on 3 aspects. The first one is related to what we had before our on-site inspection, after what we did during the mission, and at the end a few examples of the qualitative damage classification that we performed after the mission. Before to go there, we had few tools, mainly maps. The first map that we had was a damage proxy map provided by the Jet Propulsion Laboratory from Caltech in Pasadena. In these maps, the surface deformation is captured by using some INSAR technology, comparing the images, the data before and after the event. In these pictures, you can see how this map looks like, and a zoom around the Arquata del Tronto town. That is the one that I will show you later. Other maps were available from an European project, the Copernicus project, that was based on satellite images. In particular, we had two types of maps: reference maps that were based on images available before the event, in order to have an idea of how these towns looks like before the event, and grading maps that were based on the images right after the event, and that they used for a classification of the preliminary classification of the damage level. During our on-site inspection, we visited around 35 villages, and we took a high-resolution photo with the geotag. Thanks to this data, we were able to define few damage classification. The mainly that we did was based on the Department of Civil Protection, the DPC, that is an Italian association, that allowed us to select to have 5 different level damage. The first one, D1, was relative to just few cracks on the structure after the event, and the most severe one was the D5 that correspond, of course, to the complete collapse of the building. In order to have an idea of how we identify this level of damage, here you can see 3 examples from the same town, that is Arquata del Tronto. And for the site 1, you can see that we have just few cracks on the buildings, so we assigned to this building the level damage D1. The second site was not so far from from the first one, and was, and as we can see, we have diffuse cracks along the surface of the building, so we assigned the level damage D3 for this site. The third image is that is very impressive, is relative to to one building that is just on the center of this town, Arquata del Tronto, and of course we assigned D5 because we had the completely collapse of the structure. After that, we had also qualitative classification of the damaged building at the town level. In this case, as you can see, here we are reporting all the towns that we inspected, and we assigned 3 different colors. Green for the villages that were not affected by the earthquake, the yellow for the moderate, the village where the damage was moderate, for example, was the case for Tufo. And the last one was the red, of course, severe damages. That was when the damage was affecting the most part of the town. That can be the example, of course, for Amatrice. And this was my last slide. Thank you for your attention.
So the GEER reconnaissance had several phases, and what we're going to hear from next is Professor Sextos from University of Bristol. And he's going to talk about the third phase investigation, in which detailed inspections were done in several of the villages. And there was an audio problem with his video, so we're actually going to have it played through this iPhone.
Well, we have the audio at one end and then the video at the other.
Okay.
1, 2, 3.
name is Anastasios Extos, and I'll be very happy to present to you even through video, as it's currently almost midnight in the UK. The methodological steps that we followed for structural inspection in the affected area. Our team was comprised by structural engineers, some of those also member of GEER, coming from the University of Bristol, NTUA Athens, Aristotle University of Thessaloniki in Greece, that's the Hellenic Association of Earth Engineering. So we'll be showing you some slides from the inspection procedure, as well as some indicative results and some ideas for future inspection. So, in short, the way that we proceeded was the following. First of all, this was a two-stage field mission, in the sense that geotechnical experts led by George Milonakis visited the site in mid-September, right after the event. Structural engineers followed early October. Now, the question always has been, as you see the map of the visit, of the places that we visited, but the question is always where to go first. One way to deal with this is to install or download the Copernicus files to see a first estimate of the collapsed buildings. But also you need to collaborate with, and this is what we did in fact, with the GEER people and the other survey groups to make sure that there is no significant overlap between the places that we were planning to visit and the places that had already been inspected. Having done that, we started a campaign of building by building inspection to perform a complete observation of the area and identification of the most interesting from scientific or engineering point of view in the areas that were most important to be inspected. Geolocalization of photos is something very important in order to be able to deploy the information on the map and then make any correlation with in terms of spatial distribution of excitation and response. So coordinates are saved and geotagged, photos are shot by all members of the mission, and then in post-processing these are being further cleared. But the idea is that we have either a GPS device with us to complement the photos who have embedded GPS tagging anyway. So there's always a duplication of effort in terms of the information that we gather and geospatial information that we collect. Then it was very important to get familiar with Italian quick inspection form, which is based on the IDIS form. In short, this is a general approach for post-earthquake damage inspection and safety assessment of structures, dealing with the structural system, the material, quite detailed examination of local damage, as you can see in the figure below, soil conditions, various roofs, foundations, and any other kind of damage that is being identified. So that inspection form was transformed into an access database for our tablets, which were also equipped with GPS so that they could trace the signal of the exact position. And every building got a unique ID for further processing. Naturally, we also did it on pen and paper just to play safe in case that there was any error in the database or the GPS tagging. It's always a good way to play safe and have some redundancy with it. Typologies of the structure. Of course, this is an area where most of the structures were not really seismically designed and constructed, and they were pretty much ductile. And the reason was that most of them were quite old buildings, with the exception of those who had been retrofitted after the 1997 Umbramark earthquake, mainly in the northern part of the affected region. So the two main typologies that were identified were masonry buildings and reinforced concrete buildings, let's say at a ratio of 4:1 or so. And this was also reflected in the data structural data that we've got. Another important aspect of the work as a following stage is to correlate the post-quake with pre-quake photos that are available in Google Street Views. And this is very useful, particularly when we need to understand a little bit better of the structural system of a partially collapsed structure or even a totally collapsed, because otherwise there is no way to identify the number of stories, the area, the footprint, and the structural system. So this is very, very important to engage with Google Street View. You can see here some before and after, images, which were pretty handy in dealing with this aspect. And then, this is something that is not really described in the Italian inspection sheet, even though the information is quite extensive in terms of local damage. One needs to define an algorithm or some weighting scoring to assess a global damage state for the structure, and this is what we did automatically. Then, shape files containing the surveyed building footprints and associated data from the database were generated, showing the distribution of the various damage states and in some specific cases, quite selectively, about 20% of the sample, the ideas was retrospectively completed based on the existing photos, pre-quake images, building footprints, and engineering judgments. So in areas that we needed just few buildings to populate our sample better, we retrospectively used photos of other groups that did not exist. They did not contain detailed information, but as I said, we, by engineering judgment, we managed to do so. Another step was the validation of the database, particularly in the Amatrice red zone, because of course our mission was was applied 1 month earlier than the event, which means that sometimes it was difficult to identify whether a collapsed building was immediately collapsed after the earthquake, or this was a result of a demolished, partially collapsed building. So this again involved previous images of the Copernicus database to make sure that whatever we record in the database as full collapse was earthquake-triggered full collapse and not man-made. Now there are a few other aspects that are still open, like which shape maps to use, perhaps better than we do, that INGV tends to underestimate the magnitude of the earthquake, and this is also reflected in the distribution of the intensity measures. And then another question is how reliable is Copernicus' first assessment, given that in some cases the roof from the satellite seems to correspond to a partially or collapsed building or a safe building, but at the same time there is some hidden information that you can't be inspected by the satellite. So we are doing this correlation between the on the ground, let's say, field inspection and the prediction. And another very important aspect is whether we have adequate data to perform empirical fragilities. This is something that we're still working on, populating the data, and I think that very soon we'll be able to compute these empirical fragility curves, which is quite handy information based on the existing data. Last but not least, the very recent earthquake and the cumulative damage and partial collapse or total collapse of the multiple events. Given the extent of the database that we've got, I think it's very, very useful to be able to have the evolution of damage for different events. And this has a very significant scientific importance in our opinion. So these are the acknowledgements of the various people participating under different schemes. And having said that, I would like to particularly thank Dr. Raffaele Derisi for his excellent work in pre- and post-processing of most of the data that you've seen. So thank you very much for your attention.
I'm next, right? Yep. I believe so. Okay. So, coming in from the structural engineering point of view, I think we've all seen a lot of images of damaged structures and collapsed towns. You've seen it from the drones. So our objective here is not really to focus too much on showing you picture after picture of collapsed structures. So it's more about looking at the success stories. What can we learn from this event moving forward, since we already know that poorly designed structures don't perform well during earthquakes. So we really wanted to focus on how do modern structures behave. You've already seen some hints to it for reinforced concrete structures, and also what is the effectiveness of different types of retrofit. So we're going to focus on those two topics in my presentation. I'm going to talk about reinforced concrete frames with masonry infills, which is a typical detail and type of structure in this region. The hollow clay tile is used for thermal insulation. It gets very cold in these areas. It's mountainous areas. It gets cold in the winter and very hot in the summer. And it's pretty much, it's a historical type of construction since the 1960s. And then we're going to have a second presentation talking about the unreinforced masonry buildings and different types of retrofits and their effectiveness. I'm going to go through the concrete relatively quickly because we didn't really spend too much time looking at these types of structures anyways while we were there. This is an example of two types of buildings. You've seen them already in the structure in previous presentations. This is all almost post-war, post-1960s to modern code. But the 1960s to about 2000, detailing was not quite as up to code or modern requirements as it wasn't then as it is now. So you'll see a lot of these structures have poor detailing in the connection between the unreinforced or the masonry infill, and also there's damage to the joints. These are two examples. And also what's important about these types of structures is this is where most people live nowadays. They don't live in the center of the town. These are all in the periphery, newer parts of town, much higher density of population in these buildings also. Also, we'll talk about the different performance levels. This is only an example just to show you the detail of, this is not exactly a masonry infill, but to show you the detail of the type of masonry that is the hollow clay tile details that are put inside a concrete frame. This is a detail from the hospital in Amendola, which I will show you afterwards. So most of these are residential structures. So these are the structures that have impacted most of the people. You'll see this, the building is standing. It is not a collapse. There can be serious problems to the beam column connections in the first two floors, but this is really what affects most of the population in these towns. The older parts of towns, there's always a much lower density population. This is high density areas, and you've got these, it's not a collapsed structure, but you can't really use these types of buildings. So most people get displaced because of it. When masonry, you have hollow clay tile masonry, but you can also have much stiffer, it's almost a confined masonry detail. Now you've got a much stiffer structure within a flexible concrete frame, and it's a double-edged sword because you've got the stiff structure that is going to damage your joints, but in this case, for example, it didn't collapse, at least it's able to hold the gravity loads. There have been in Amatrice an actual collapse of, and probably more than this one, but this is an example of it. This is actually a modern reinforced concrete frame building that collapsed. It probably didn't collapse as much as you can see in this picture. Anytime you see the plastic do not enter rim, or whatever this is called in English, okay. Anytime you see this kind of detail, it means that there was a death there. Because you're not allowed to go into that space, and then they have to go in and actually take the structure apart. But this is an example of fatalities that have occurred in reinforced concrete structures. The bigger problem with modern construction is that it's typically mixed in with hospitals. A lot of hospitals have a lot of wings that are made of this reinforced concrete frames. They behave well in the sense of there isn't collapse, but they definitely affect usability. This is the hospital in Amatrice that had to be closed down. This is a hospital in Amendola. There wasn't significant structural damage, but there was enough damage to the outside that this wing of the hospital had to be closed down. The good thing about this hospital is they actually had to use, they didn't shut down the entire hospital because it's the only hospital in the region, but they actually ended up using one of the older wings, not the newer wings of the hospital. Big problem here, you've got this non-structural damage right here. It's pretty much, it's almost just cladding that came down, but of course this is the entry and exit way for the ambulance. So this part of the hospital was not accessible for emergency vehicles, so they had to shut it down, and actually the concrete or the cladding that came down right on the ambulance. An important lesson to be learned here, which you may see it again, the structure on the left in the presentations. The structure on the left was a retrofit structure. It didn't collapse. It's an older type of structure, but it was a police station. So now you lost usability of an important structure. So then we really have to look at what are their performance expectations. Is this an acceptable performance? Maybe it would be if this was a residence, but it's not because it's a police station. Interestingly, a lot of the clock towers you'll see didn't come down, and there's a whole other discussion as to what we can see there. But if you look at this detail here, you can see that this clock tower was retrofit, and if you zoom into this area right here, I don't know if it's pretty clear in the picture, you can see this tie that went across that is actually stretched. So this is telling me, hey, this retrofit actually held. The clock tower definitely rocked. You can see a lot of damage, but it held together. And to me, this is really the symbol of what we've learned from this earthquake is retrofit works. And hopefully this is getting communicated to the people, and especially with this latest shaking that's happened in the last couple of days, I see a strong movement from the community to push towards retrofit and strengthening, especially of important facilities such as hospital, police stations, and schools. With that, I'm going to switch over to, I think I need help with this, John, to the other types of structures.
This is the video, right?
Yeah, so it's
So use 8B, yeah. I think the audio was okay, but we need to turn it back on. Yeah. Just unclick that. And then drag it over. I think it's playing.
there's 3 different volume
Yeah.
controls.
I am an assistant professor in structural engineering at
This got unplugged.
CNSI, University of Rome, and my
What did that
main
happen?
research interests are in the earthquake performance of
See if I can.
masonry.
There we go.
I'm going to give you a short video presentation about unreinforced masonry building retrofit policy and effectiveness. This presentation was prepared with my colleagues Guido Maggenes and Andrea Penna from the University of Pavia. I am an assistant professor in structural engineering at Sapienza, University of Rome, and my main research interests are in the earthquake performance of masonry structures. The Central Italy earthquake has shown a tremendous impact on unreinforced masonry buildings, as you have seen from the previous presentations. However, we can also observe a dramatic difference in the performance among adjacent buildings. In this slide, with pictures taken in the Corso Umberto I, the main street in Amatrice, you can see completely collapsed buildings close by buildings which are still standing. And these buildings display wall anchors which are attached to steel tie rods. So for sure this type of intervention can be recommended and can have a positive effect on these structures. If we move to Norcia, where the overall performance of the buildings has been much better, we can observe the systematic use of wall anchor and steel ties. And these elements are not just the result of recent earthquakes and following retrofittings, are the effect of at least a 19th century event which caused more than 100 deaths in Norcia. Following this earthquake, one among the first building codes for earthquake-resistant constructions was issued. This standard limited the number of stories at 2 and set a limitation also to the overall height of the building. Similarly, it recommended minimum thickness for the walls and a tapered section along the height. All elements which we are able to observe still today in Norcia. At the same time, strong emphasis was put about the quality of the masonry, with recommendation of use hydrated lime and sand washed with fresh water, with the ban on round stones and the recommendation of fired clay bricks or semi-dressed limestone units. Moreover, there was the recommendation to connect horizontal structures to vertical walls and to resort to wall ties. If we observe some buildings in and around Amatrice, we are able to recognize the use of wall anchors and steel tie rods. However, we see an unsatisfactory performance. This performance is related to the very poor quality of the masonry, which has already been highlighted in a previous presentation, both due to the mud mortar and to use of round stones. Therefore, if the mortar quality is so low, even a systematic use of steel ties is not sufficient. In this other building, which was the Carabinieri, so a police station in Amatrice, which was undergoing a retrofitting intervention following the L'Aquila earthquake at the time of the August earthquake, we are able to see a systematic intervention with steel stitches. This intervention, coupled with the top steel tie rods, saved the building from the collapse, but such a building would not be operational after an earthquake, as it is expected for a strategic building like a police station. And this is an example of the limited improvement that can be expected from a poor masonry building, even after systematic interventions. Another critical point is that of the top bond beams. These bond beams have been built using reinforced concrete elements, and in the past the poor performance of the buildings displaying this type of beams was related to the lack of a connection to the below standing masonry. However, we can see in this slide two examples of shear connectors at the center of the wall section or on the two external leaves of the wall sections, which performed unsatisfactorily. However, also if steel top ring beams are used as recommended more recently, we observed a poor performance irrespective of the use of a top element on the top face of the wall or on the side of the wall close to the top, despite, in this case on the right, a very systematic connection through bolted bars. Therefore, again, the quality of the masonry becomes crucial. And this comment applies also to the use of reinforced concrete roofs as a retrofitting intervention. We have seen pancake collapses, which are certainly associated to this type of intervention. However, we can also observe buildings where the performance is much better, even if such a stiff and heavy element is adopted. And the reason for such strong differences in the performances is again the quality of the masonry. Matter of fact, if we observe buildings still possessing their timber roofs, we see that despite the use of very light elements at the top of the building, we have a collapse of the walls because the quality of the masonry is again insufficient. Among the intervention that seems to have worked on the original masonry, there is the repointing. So this technique, which recommends the removal of the original mortar from the external leaves and its replacement with a more adequate mortar. In these two examples, we see that the building behaved in a reasonable way on the left, in a very good way on the right. However, we don't know if additional interventions, so for example, injections of mortar mixes have been carried out at the same time. Another intervention to improve the masonry performance is the so-called reinforced concrete coating, so plastering the wall with reinforced plaster, where the reinforcement is a welded mesh. When this intervention is carried out just on the inside, the performance is usually inadequate. Whereas if the intervention is carried out on both sides, we see a much better performance. In this other case, we are in front of a building which in the mid-80s was demolished, and its stone units have been used to build a new one with a modern mortar. At the same time, reinforced concrete ring beam, both at floor levels and at window opening, were introduced, and the performance was very, very good indeed. This building is in Castelluccio di Norcia, was again completely rebuilt. Here on the left you have the Google Street View 2011 screenshot, whereas on the right you have the building as it appeared last September. And you can see that there is no damage in the building, but at the same time there is no sign of any wall anchor. This is because the stonework is just a cladding, and the actual structure of the building visible from this hall is that of a modern mason with hollow clay blocks. The stone cladding was then connected to the structural masonry through these rebars. However, this kind of intervention, which was very effective from a structural point of view and is able to save the ambient appearance of this historical center, can be called into questions by architectural restorers. And there are some issues about the durability of these rebars unless stainless steel elements are not used. I would like to thank you for your attention and leave the stage for the next speaker.
So I think this last talk raised a few issues that we can go on all day talking about all the different issues that are raised, but he really brought up the point of authenticity. It's very important in Italy to maintain the look of these towns, and so it's the balance of keeping, having structures that can withstand earthquakes, but also keeping the spirit of what the town actually looks like, because main source of income there is tourism, and you lose that look, you lose the authenticity as he raised the issue. The other thing, the problem with the structural engineering is that the cameras go past the buildings that stand, and it's difficult to know what kind of retrofit was done to those buildings, and it's very difficult to pay attention to those. We're all drawn to the structures that have collapsed. So it's an ongoing job with the structural engineering. I'm going to switch to another aspect that was important to the EERI team, and it's important lessons to be brought back to the U.S. is the emergency response and recovery. This is definitely something, we have drills in the United States. In Italy, they just have real earthquakes that happen every few years. I was looking at videos in my past history. I was living in Italy in 1980 when there was a big earthquake down south of Naples. And so I've gone back to look at videos, and the biggest problem there was these were not only poor towns, but there were some smaller towns that were not getting the media attention, and the response was slow. So you see these videos where people actually had to go and rescue people themselves. So the survival rate was definitely lower than we have in these newer events. It's a big program in Italy. This emergency response, Italy is a very small, geographically small country, but it has a large population, and it's got everything. It's got mountains, and it's got earthquakes, and it has flooding. There's a disaster around the corner because of the high density population. Because of this, they have a very strong infrastructure, and with every earthquake, they learn something, what to do for the next disaster. For example, and you'll see the pictures of these tents. Every region in Italy has its own warehouse of tents and equipment that they're ready to deploy within a few hours to affected regions. It could be up in the Alps because of flooding, or it could be central Italy or anywhere else in Italy because of earthquakes. So there's different levels of response. There's the emergency response, which I separated from the immediate response, even though the emergency response happens within hours. The immediate response is, still short-term in terms of hours and days. Viability, what is accessible, what isn't? How do you make the roads viable? How do you inspect and make sure that you keep people optimized? You can't just evacuate everybody from everywhere, just really optimize what to do with the population. What to do with the population short-term in shelter. I'll show you some very impressive pictures that I am hoping you've already seen in the media. And then looking at long-term recovery, which is always the hardest thing to do, especially in Italy, because as they're planning on one long-term, or they're working on one recovery in one region, there's another earthquake somewhere else, and so the resources need to be spread out. And then there's a short video that I'm going to show you about this risk mitigation program and raising awareness to the public. So the Department of Civil Protection falls under pretty much the national government, and they take over after an emergency. I have a presentation that I'm only going to show you some highlights of the response that they've done to this event. There were a population of 35,000 people were displaced or affected by the earthquake of the August 24th. Within hours, if not minutes of communication, the local and state-level authorities convene and start organizing and planning and moving forward. It's a very, very efficient and effective system. As you can see, by 4 o'clock, they're already starting, within half hour of the earthquake happening, communication systems internally were already moving forward. First step is the search and rescue. It's fascinating there's a picture up on the top right. They have these dogs that are trained to detect bodies. They can actually smell maybe even just a few hairs, and they're able to distinguish whether it's a person. Somebody spent hours explaining this to me, between a person or just a towel that somebody had used. They bring in 2 different dogs, or they can have x-rays or just different machines, but the dogs are the most reliable means. But they have to have 2 different dogs coming in and both agreeing that there's something in that spot, because it's really dangerous in the rescue if you try to save somebody in one spot, but then you're actually causing problems, and there may be someone else nearby who is alive. So this is all things that happen within hours. You'll see a lot of demolition that you think is actually damage, but it's actually search and rescue coming in and trying to get people out of the towns and getting people out of that are trapped in the buildings. The next step is the immediate response of, one is infrastructure. Luigi already talked about the different bridges. It was amazing. We were there 2 weeks after, and we're driving on this bridge, and it looks perfectly clean, but you can tell as you get on, you go thump, and as you get off, you go thump again. That means that bridge was actually damaged, and they actually went in and repaired it within a few days, especially because there's a main road that crosses the mountains from the eastern part of Italy to the western part of Italy. So those are vital. Cultural heritage. They actually have to go into these buildings, a lot of churches, and rescue artifacts. It's fascinating to see the process they have to go through very, very carefully, and large number of people associated with that. And then deploying everybody and as many engineers and units to go out and inspect the buildings and check viability of the different infrastructure, as well as towns, and determining what to evacuate and what to not evacuate, again, in schools and hospitals. There's an actual term, it's a tendopoli. It's these towns, tent houses or tent homes. You can see here up on the hill is the town of Arquata del Tronto, and they have, and you can see it in the map, there are tendopoli all over the region. They really want to keep the people close to their centers where their home was. They don't want people to start leaving and moving out, even though this was a special event because most of the towns affected were people's second homes. So a lot of people just went back to their homes. So they didn't have, at the peak, they only had 4,200 people living in tents, and with time they've put them in hotels, or actually they've gone to family homes and they've moved everybody out. You can see the plastic tarp, it was raining. So they have to deal with weather. Big deal with the earthquake that happened 2 days ago. They cannot and will not build these tendopoli because the winter's coming. It's too cold. So they're looking to put people on the east coast of Italy in hotels. But the speed, these were up within the end of the day that this happened. So the people had places to go. You will see these these buildings, long buildings at the edge. Those are the schools. They actually built the schools right in the same place because that was very important to the whole resiliency concept. School was starting middle of September, and they wanted to make sure that they could get as many schools started within, hopefully by the same time as the rest of the country was starting school. Interestingly, we had lunch in one of the shelters just as the people and the residents and even the assistant mayor lived in the tent. They have the same tent infrastructure for all the army and the police and all the aid that comes in. So we actually had lunch with the aid people there, and it was fascinating to talk to the different people and see what's going on. The important thing, again, is about community resilience. So getting people out of tents and putting them in temporary shelters, either hotels or building these. It's funny, they call them casette. They call them tiny little houses, the little houses that we live in, just wooden houses. They call them tiny little houses. So they're trying to put people into this temporary shelter. Fascinating story that we can talk about for hours is this set of buildings here on the bottom right of the picture. The region of Friuli-Venezia Giulia, which is up in the northern eastern part of Italy, that was affected by a big earthquake in 1976. And it's actually the big success story because it's in the north and they're richer and they were able to rebuild the cities. They actually recovered very well. Well, they have a program at the university there of building this temporary housing and temporary schools. And there was just a project, and they actually deployed these temporary prefabricated buildings, and they opened the school in Amatrice Elementary School. It looked really, it's hard to see it in this picture, but it's a whole new school, prefabricated buildings, and school started on the day that the rest of the country started school. So that was a big victory in getting the resiliency and the whole community moving forward. You don't want people to leave the homes or their towns. You want to keep them locally, but you also want to be able to rebuild, and it's a whole long, messy process in Italy. And so to that aim, we went to see L'Aquila, that I had visited right after the earthquake of 2009. So this was 17 years later, and it is a huge construction site. There's a lot of activity going on, a lot of retrofitting, a lot of rebuilding. Fascinating, though, because if you look at this picture right in the middle, there's some serious shoring going on, that they know these buildings are going to be up without being rebuilt yet for many years, because it just takes a long time to get the city rebuilt. Interestingly, though, everybody's moved out of the center of the town. They've rebuilt the more modern, higher density homes outside of town. And so when we actually drove through the ghost town of L'Aquila, we hit the center, and people actually doing their stroll down the main shopping street, even though there are no shops. People are still coming, walking into the center of town, doing their stroll, going to, this is a church that is seriously damaged on the inside. It all imploded, but there's a coffee shop and ice cream shop right next to it, and everybody was there as if that was just the normal way of going. And so there was a big signs about L'Aquila being reborn. It's really moving forward in coming back to life. So this is really looking back 7 years, which in glacial ages, I don't know if it's enough time yet. But this is the norm in Italy, is just there's a disaster and just trying to pick up and move forward again. So that's the end of this part of the presentation. The next part is talking about, everything is more reactive in what we try to do, which they have to do because of one emergency after the other. But there's actually now, and thanks to just the internet and people now learning more and more about earthquakes, as I said before, really moving forward to a more educated and more willing voter force that can actually move things forward in improving resiliency of the country. And here's a program.
Good afternoon. I'm Angelo Masi, Professor of
I think it's
Structural
interesting.
Engineering at the University of Basilicata and a member of the Board of Directors of the ReLuis network. I shall represent the Italian communication campaign on natural risks, I Do Not Take Risks. It is a communication campaign created and promoted by the Italian Department of Civil Protection, the National Association for Public Assistance representing the voluntary sector, the Institute of Geophysics and Volcanology, and the network of the University Laboratories of Seismic Engineering. The campaign process includes 3 main phases. A first phase defining the campaign messages and the preparation of informative material, a second phase related to the training process, and the last phase, which consists of a 2-day information campaign carried out in the main square of each involved town. The rationale behind the campaign is that preventing or at least reducing the dangers associated with earthquakes is everyone's interest and duty. Learning how to do so through an effective diffusion of information on seismic risk fosters collective and individual responsibility while encouraging active participation. The campaign is targeted at ordinary citizens, therefore it is carried out in the squares of the towns where they live and work. Volunteers are the main actors of the campaign. They inform citizens with simplicity, treating them as equals, serving as living examples by not only teaching prevention but practicing it. The volunteers involved in the campaign generally live in the places where the campaign is carried out, and their permanent presence emphasizes that prevention should be an everyday activity. Moreover, volunteers often know of and spend time with vulnerable population groups, for example, disabled people, who generally have the most exposure to risk and the least access to other communication campaigns, for example, web campaigns. The scientific community contributes to the campaign through the competent centers of the Civil Protection Department. Researchers train volunteers, transferring them basic concepts on seismic risk through language and knowledge as simple as possible, thus enabling volunteers to effectively transfer information to common people when they meet them during the campaign. Simple patterns and images are used during the training, as an example clearly showing the role of vulnerability in determining different damage. Volunteers distribute informative materials and answer citizens' questions on the possible ways to reduce seismic risk. The informative materials consist essentially of a leaflet and a card. The leaflet deals with prevention aspects. It explains in clear language what the citizen needs to know in order to reduce the effects of an earthquake, describes some simple measures that everyone can carry out, and provides some suggestions about more technical measures requiring the support of an expert technician. The card deals with emergency measures. It contains simple, useful information for families on what to do during and right after an earthquake. The card can be hung on a wall or a door in plain sight so that the proposed suggestion can be promptly and automatically applied in the case of an event. The first edition of the campaign was held on 22 and 23 October 2011 in the main squares of 9 Italian towns located in high seismicity zones. The encouraging response of citizens and volunteers during the first edition of the campaign clearly showed that a new way of communicating was being created and that volunteers could effectively reach ordinary citizens in such a process. Further, this proved to be a very starting point to launch an integrated campaign, including other natural risks with the same branding and communication tools. Specifically, the tsunami risk was added in 2013 and the flood risk was added in 2014. Up to 2015, about 10,000 of civil protection volunteers have been trained and about 1.5 million of citizens have been contacted in several hundreds of Italian towns. The 2016 campaign activities, which were carried out in about 700 squares on October 15 and 16, are being recorded and relevant data are still being processed. During 2012, the campaign was implemented also during the seismic war that affected the Pollino mountain range in southern Italy, to help people cope with the swarm and to prepare for large events that could occur in the future. The citizens reacted well during the main shock of the swarm, demonstrating that the preparedness and communication activities play an important role in building and enhancing a positive public response. The experience of the first 6 years of the I Do Not Take Risks campaigns confirms that risk communication and awareness are crucial to building social capacity and to help citizens effectively cope with natural hazards, being informed, aware, and finally active. The campaign is due to the work of quite a lot of people, and I wish to thank all of them for their passion and above all for the example they set.
And as a testament of the success of this program, somebody posted on my Facebook page a screenshot of one of these programs, just somebody completely independent. So the information is getting out to the people and raising awareness of the event. Pass the words to you. Thank you.
Thank you, Sylvia. Okay, so we are at the end of our briefing. I'm going to have just a few closing remarks. I think I want to begin the end by thanking the many volunteers who participated in this reconnaissance effort. Nobody gets paid for this. This is entirely a volunteer effort. These people are taking time out of very busy schedules, doing very difficult work. And so I want to thank all the volunteers from all the different organizations that participated. And I particularly want to thank the speakers, the remote speakers, and those who were here today. Great job, and thank you very much. I'm going to just have a few final thoughts on what comes next. You've heard about reconnaissance, what actually happens after that, and what are some of the major lessons learned that we can take moving forward. So what you need to understand, for those of you who are not earthquake engineers or seismologists, is that our profession is experience-driven. We learn from our failures, we learn from our successes, we gather data, and we move forward. We need observations. In that sense, it's sort of like medicine. Medicine is also an experience-driven phenomenon. If you go get a drug that's prescribed for you, that drug has been tested on many people and animals and things previously to show that it works. It's kind of the same way in earthquake engineering. We have to see what works, and then we adapt as we go forward. And really, reconnaissance is how we get that experience. It's how we learn from what's already happened. So this task of conducting reconnaissance is absolutely essential. It's at the core of earthquake engineering and also of much of seismology. when we think about what we learn out of reconnaissance, in some cases we're looking at engineered structures. So we designed a structure a certain way, we see how it did, maybe it did well, maybe it didn't do well, and we learned something about the effectiveness of our methods and our practices through that. And there was some of that in Italy. But a lot of the data that we gather from earthquakes is not from engineered structures. It's the natural ground, or it may be structures that were before the era of at least modern engineering. But data of that sort is also extremely valuable, and it really forms the basis of the techniques that we use to estimate risk, whether it's ground motions or collapse of structures or the falling of rocks off of hills. We have to gather the data in order to estimate the risk from future earthquakes. So specifically, what's going to happen next is a report. So we already have a version 1 report that was published a little over a month ago. A version 2 GEER report is in preparation, probably about 75 or 80% done, and should be ready in early November. We also will likely be doing some kind of joint publications with all the other research organizations that participated for this event. So that's from a GEER perspective. Some of the subsequent research utilizing the data that you've seen here today will include structural fragility, and you heard Professor Sextos refer to that. We can learn from this event in terms of source characterization, particularly in Italy. The data from the surface faulting directly goes into models. You saw a little bit of that in Professor Kahn's presentation. And the ground motions. As a well-recorded event on a normal fault, there aren't very many of those. I could probably count on one hand how many well-recorded normal fault earthquakes we have, and so that data will certainly be very useful as we go forward. Some of the key lessons. I put this slide together with help of Paolo this morning. We had the Umbria Marche earthquake up here in '97. I'm showing here not the overall area. There was broader region with aftershocks, but this is essentially the finite fault model for that event. Here's the present earthquake. Here's the L'Aquila earthquake. And you have in between here gaps. Okay? And we had, as you know, earlier this week, an earthquake right about in here. And so when we have a sequence of earthquakes along a fault system like this, one can anticipate that in the regions in between, you may have an elevated level of risk. Speaking in a very general sense, when we have an earthquake, one could say, well, the stress has been relieved because the earthquake occurred. That lowers the stress locally. So maybe the probability of an earthquake is down, at least locally. Or you could say the probability of an earthquake is higher, particularly in the regions in between. And there's a mounting level of evidence that oftentimes that probability is in fact higher, and the earthquakes this week reinforce that. Then there's this issue of segments. This was mentioned by Paolo earlier. So before this earthquake, these were a series of faults, and there's many more as you go north and south. So we have these faults that were mapped, which are essentially segments along a very long structure. And in many places around the world, as we think about future earthquakes, where earthquakes can happen as we look forward, it's often confined to the domains of these segments. Yet what we see as we look at earthquakes in California, certainly, in Japan, and this one in Italy, is that the notion of an earthquake confining itself to a segment is not the norm. In fact, it might even be the exception. It's very common for earthquakes to rupture multiple segments. Now, the Italians are arguing amongst themselves whether these should have even been two separate segments, and so there are scientific debates of that sort. But the notion that multiple segments can rupture in a single event is pretty much established science at this point. We're doing that routinely in California, and it's something that needs to become more of a standard practice worldwide. I would say this earthquake was not a surprise. It was not a surprise with respect to the gap. It was also not a surprise with respect to the level of ground shaking that occurred once it triggered. So we could have anticipated high level of seismic risk in this area, and we could have anticipated the level of ground shaking that would occur. And of course, as you've seen, there are many villages that were subject to that shaking. Some of those villages experienced some retrofit, many did not. When there isn't preparation, there isn't retrofit. Even though you know that there's a risk, the consequences are pretty dire. And we had 300 fatalities, many tens of thousands of people displaced, as Sylvia was discussing. But there's hope as well, as you've seen in some of the prior presentations. When we know there's seismic risk and we take action through public policy, investment into retrofit, it is possible to have success, even in the presence of masonry structures and structure types of that sort. So we can solve this problem. This is largely a matter of political will. We can forecast the risk, we can fix the problem, but we need the mobilization of public interest to get behind this and make things better. And one of the things that's encouraging here in Southern California, we haven't had an earthquake, a major earthquake, since 1994 Northridge, and yet we've seen some movement in this regard in public policy and movement towards retrofit, even without a recent disaster. And that's really what we need. We need to be able to mobilize action, even when we haven't just had a disaster. And hopefully that's a message of hope that we and others can have moving forward. With that, I'd like to close the webinar, and thank you very much for attending it today.